All right, so hello, grade 11 university physics students. This is Mr. Musklow, and I thought that it would be helpful for me to just record a video of me explaining the material in today's lesson, since I'm not there. I don't always do this, so don't expect me to always do this when I'm gone. But there has been situations in the past where I know well in advance that I'm going to be away on a certain day. And it honestly doesn't take that long for me to just record a video. I have some software to record the screen on my computer. So it doesn't take me long to record these videos, and that way students don't miss out on just me explaining the day's material. So this video is actually on YouTube. I do have a YouTube channel. It's called Mr. Musklow, and you're welcome to subscribe to it. You'll see that my YouTube channel has some videos from the past where I've done this before. So there's just basically videos about like random topics that I've been teaching while I'm away. In our first year of COVID, I actually had to isolate for a few days. Not because I was sick, but because I was a contact. So I recorded some videos while I was gone. So anyways, it's just a video of today's lesson. We're learning today about electromagnetic induction and Lenz's law. So the law of electromagnetic induction might sound kind of intimidating, like it has a complicated name, but it's actually a rather simple idea, as we're going to see. And it's also a very important idea, actually. As it says in the handout, the law of electromagnetic induction is actually the principle that's used to generate almost all electricity in our electrical grid today. So we're going to learn the details of how electromagnetic induction is used to produce electricity in our next lesson. In this lesson, we're just going to learn what the law of electromagnetic induction says. So this lesson is just about the law itself, as well as a related law called Lenz's law. And then yes, in our next lesson, we're going to learn how electricity is actually generated in our electrical grid. So we'll just get right into it then, what the law of electromagnetic induction says. It simply says that a changing magnetic field will induce a current in a wire that is immersed in the magnetic field. Now, to just better understand exactly what that law means, students are often asked to imagine a magnet being plunged into a coil of wire, because it's this scenario that can just help us understand this law better. So you can see that in this image, we have a coil of wire that's just wrapped around a hollow tube. And this coil of wire is not connected to a battery. It's connected to an ammeter. And an ammeter is just a device that measures electric current. So there is no battery hooked up to this coil. And in this setup, we are plunging the north pole of a magnet into the coil. So we're just pushing it into this hollow tube, plunging it into the coil. Now, since the magnet is moving into the coil is immersed in a magnetic field that is changing. And so the law of electromagnetic induction says, therefore, that a current will actually be induced in the wire. And so the ammeter would register a current as a result, because there would actually be a current induced in the wire when the magnet is plunged inside. Now, part of the reason why I wanted to record a video of this lesson is because I think it's actually helpful to just see the law of electromagnetic induction in action. You might have noticed that I use some PhET simulations. So our trusty PhET simulations are making a comeback. This PhET simulation does not involve wiring things into circuits. Here, we're actually plunging magnets into coils of wire. So we get to actually see electromagnetic induction in work here. So you can see that in our PhET simulation, we do have a coil of wire. This time, though, it's not connected to an ammeter. It's connected to a light bulb instead. So in our handout, it was connected to an ammeter. We said that the ammeter would register a current. A light bulb is better for visual purposes, though, because a light bulb lights up whenever a current moves through the bulb. Now, you'll notice that the bulb is not on right now, and that is to be expected, because right now, the coil is not immersed in a magnetic field that is changing. It is immersed in a magnetic field. I can actually turn on our field lines, and we can see that our bar magnet has a magnetic field around it, as we expect. But an important thing to understand about the law of electromagnetic induction is that it isn't just a magnetic field that induces a current in the wire. It is a changing magnetic field. So right now, there is no current induced in the wire because the magnetic field is not changing. But I can change the magnetic field by moving the magnet. And so if we plunge the magnet into the coil, we should see the light bulb light up, since that changing magnetic field will induce a current in the wire. So let's do that. I'll just plunge the north pole of our magnet into the coil. And you can see that we did get a bit of current, so the light bulb did light up a bit there. Now you can probably guess that if I move the magnet in the opposite direction, that will also induce a current. So here I go. You can see that the light bulb lit up a bit again. And so now I'm just going to move the magnet back and forth and back and forth. And we should see the light bulb light up while I'm moving the magnet back and forth. Okay, so the important idea here is that the magnetic field needs to be changing for a current to be induced in the wire. So again, right now, the magnetic field is not changing, so no current is induced. We need to change the field by moving the magnet. Okay. So yes, that is a point that I try to make clear in the handout, which is that the magnetic field has to be changing. If the magnet is stationary, then no current is induced in the wire. Now, there's really two factors that affect how much current is induced in a wire. So as explained in the handout, one factor that affects the amount of current induced is the number of loops in the coil. And we can actually see this in our PhET simulation as well. I'll just go back. So you can see now that we have a coil with only 2 loops. This coil has 4 loops. And so it turns out that if the coil has more loops, that will result in a greater current. So hopefully we can see that if I move our magnet back and forth again. So here I go, moving it back and forth in our coil with 4 loops. And then this is what it looks like moving it back and forth in just 2 loops. And you can see that we're not getting nearly as much current. So the number of loops in the coil matters. The more loops that you have, the more current is induced in the wire. So that's one factor that affects the current. Now, the other factor that affects how much current is induced in the wire is how rapidly the magnetic field is changing. So if I change the magnetic field more rapidly, that will result in more current being induced. So in this setup, how can I make the magnetic field change more rapidly? Well, I can do this just by moving the magnet back and forth more quickly. If I move the magnet back and forth more quickly, then that's going to change the magnetic field more rapidly. So here I go. I'm just going to move the magnet back and forth quickly. Now, if I move it back and forth more slowly instead, you can probably expect that we're not going to get as much current. Okay, so that's the other factor that affects the current in the wire, is just how rapidly that magnetic field is changing. Okay, and that's the law of electromagnetic induction in a nutshell. If I was giving this lesson to you in person, I would ask at this point if there are any questions. But this is a pre-recorded video, so I can't do that. But hopefully that made sense. All right, so in the remainder of the handout, we're going to learn about Lenz's law, which is used to determine the direction of the induced current. So we've learned so far that yes, changing magnetic field will induce a current in a wire. But we haven't talked at all yet about the direction of the induced current. And it was a Russian physicist named Heinrich Lenz who worked this out. His argument was actually very simple. And in fact, if I just gave you the task of determining the direction of the induced current, I'm sure that you could figure it out as a class, because the argument does make some good sense, I think. So this was the essence of Lenz's argument. Let's imagine again that we are plunging the north pole of our magnet into a coil of wire. And let's just pretend that we don't know the direction that the induced current moves. So let's just imagine first that it moves in this direction as one possibility. And let's see what that implies. There's really only two possibilities, of course. It can either move in this direction or in the opposite direction. So let's just start with this direction and see if this makes sense. So Lenz reasoned that the current cannot move in this direction. It doesn't make sense. And I'll explain why. The induced current will create its own magnetic field. This is an idea that we haven't really talked about yet, but this very much happens. So we've said that when you plunge the magnet into the coil, a current is induced in the coil. Now, if a current is induced in the coil, that current is going to create its own magnetic field. And so we have a name for this in physics. It is called the induced field. And in this scenario, we're dealing with a coil of wire, right? So if we have an induced current that moves through that coil of wire, that induced current is basically acting like a solenoid. So earlier in this unit, we said that if you put a current through a coil of wire, we call this a solenoid, and a solenoid generates a magnetic field. So in this scenario, we have a current moving through our coil, and so that is going to generate a magnetic field in the same way that you get a magnetic field from a solenoid. Now, we've also learned that the magnetic field from a solenoid looks a lot like the magnetic field from a bar magnet. And we can use our right-hand rule to determine the direction of the magnetic field. So I can't really like, show this to you with my hand. I can't put my hand in the screen here, but if we just imagine lining up our thumb in the direction of the current, then our fingers would curl in the leftward direction inside the coil. So you can use our right-hand rule to determine that the magnetic field from the induced current points to the left. And so that would mean then that the left end of the coil would be a north pole and the right end of the coil would be a south pole. Now, the problem here is that the right end of this coil has become a south pole. And so that south pole is going to attract the north pole of this magnet that we are plunging. And Lenz knew that this just doesn't make sense. I mean, if this happened, then the induced south pole would attract the magnet and speed it up, which would cause the magnet to induce a larger current. That larger current would speed up the magnet further, causing it to induce a larger current, which would speed up the magnet further. And I think we can agree that this does not really make sense. This actually violates the law of conservation of energy because you're basically creating energy out of nowhere in this scenario. So based on this argument, Lenz just said that the current has to move in the opposite direction instead, because this direction doesn't make sense. So if the induced current instead moves in this direction, opposite to what we said before, then the right end of the coil becomes a north pole. And so that induced north pole is going to repel the north pole that we are plunging into the coil. And so we have a situation here where you are plunging the magnet into the coil, and the induced magnetic field is kind of working against you. So you have to push against that induced magnetic field for the current to be induced in the wire. So that is Lenz's law. And so if we just want to kind of summarize what we've learned from this analysis, Lenz's law is written in italics here. I'll just read it out loud. So Lenz's law says if a changing magnetic field induces a current in a coil, the electric current is in such a direction that its own magnetic field opposes the change that produced it. In that wording, I think it's perhaps a little difficult to really, make some sense of what this means. So I just like to think of it instead in this way. The coil will just oppose whatever the magnet is doing. So if we want to plunge the north pole of the magnet into the coil is going to oppose that motion, and it's going to generate a north pole on its right end to repel the magnet that I'm trying to push into it. So the coil is just going to oppose whatever you try and do with the magnet. That's basically what Lenz's law says. Okay, so that is Lenz's law. And that actually wraps up the lesson, really. We learned in this lesson about the law of electromagnetic induction, which says that a changing magnetic field will induce a current in a wire that is immersed in the magnetic field. And then we also know now how to find the direction of that current using Lenz's law. Now, I'll just make a comment and say that you're probably finding that there are a lot of kind of rules to remember in our electricity and magnetism unit. We have one right-hand rule for determining the direction of a magnetic field. We have another right-hand rule for determining the direction of a force that acts on a wire with a current in a magnetic field. And then now we've learned about this law of electromagnetic induction, which has its own way of finding the induced current. So I can appreciate that our electricity and magnetism unit does have a lot going on in it, and I think that's why some students don't really like this unit, to be honest. Because I've heard from students in the past that they just find that it's a lot to keep track of. And this is part of the reason why I've been trying to include lots of examples in our handouts that give students opportunities to just practice applying these ideas that we've learned. So the back of this page has some examples for you to try. Your task is to determine the direction of the induced current in the coil, and then to also just label the magnetic poles on the coil. There are 8 examples, and I'll post the answers in Google Classroom so that you can check your work. I would very much encourage you to just try and do this yourself first without checking the answers. So try it yourself and compare your answers with your peers. And once you've done it and compared your answers, then you can check to see if you're right in Google Classroom. Because that's really the best way to make sure that you're really understanding this idea. Because it is a little tricky. Like I say, it does make sense, but it just takes some practice to apply Lenz's law. Okay, so again, I would ask at this point if there are any questions, but this is a pre-recorded video, so hopefully that made some sense. Obviously, if there are any questions, I'll be happy to answer them when I see you all again. But I suppose I'll just leave it there. Good luck, and have a good rest of your day and a great weekend. And I'll see you all next week.